Hello everyone, and welcome back to the Fluctus Channel. Unmanned aircraft began as experimental machines long before the word drone became common. Early radio-controlled targets, wartime trials, reconnaissance aircraft, and remotely piloted systems all pushed the same idea forward. Sending a machine into dangerous airspace when sending a pilot would be too risky. Over time, cameras improved, satellite links expanded, engines became more efficient, and unmanned aircraft moved from test ranges into everyday military operations. The RQ-4 Global Hawk represents one of the largest and most capable results of that evolution. It is not built like a fighter. Its shape is closer to a high-altitude glider with extremely long wings, a rounded nose, a slim body, and a single engine mounted above the rear fuselage. Its mission is endurance, not speed. The rounded nose holds powerful sensors that allow the aircraft to look across wide areas from high above the weather and many short-range threats. The long wings provide lift and fuel efficiency, while the tall tail and compact landing gear help the aircraft operate from long military runways. Every part of the design is built for staying overhead, collecting information, and sending it back to commanders far away. Inside the control environment, the idea of a cockpit changes completely. The Global Hawk has no pilot seat on board. Its cockpit exists inside a ground control station where trained crews monitor screens, maps, aircraft status, sensor feeds, and communications links. Pilots command the aircraft through computers, while sensor operators manage the intelligence collection. The crew must think like aviators, even though the aircraft may be flying hundreds or thousands of miles away. Setting up the aircraft for a mission begins with maintenance. Airmen inspect the skin, wings, antennas, landing gear, tires, engine intake, flight control surfaces, fuel system, and sensor areas. Panels are opened, tools are laid out, laptops connect to aircraft systems, and technicians check for faults before launch. Because the aircraft can remain airborne for such long periods, small maintenance problems must be found before they become mission failures. At deployed locations, crews work around the aircraft with the same discipline used on manned aircraft. Ground teams tow the drone, position support equipment, remove covers, inspect moving surfaces, prepare fuel, and coordinate with operations personnel. The aircraft may look quiet on the ramp, but it is connected to a wide network of maintainers, mission planners, weather teams, intelligence units, and controllers. Operations demand patience. The Global Hawk climbs to high altitude, follows a planned route, collects imagery and signals, then transmits data through satellite communication. Instead of a pilot reacting from inside the cockpit, remote crews manage the aircraft, while analysts use the information to build a clearer picture of the battle space. The value is not in dramatic maneuvering. It is in staying long enough to observe what others cannot. This is why the RQ-4 became vital to modern reconnaissance. It can watch borders, coastlines, deserts, shipping lanes, and areas of military interest for hours at a time. Before troops move, before ships enter a region, and before aircraft strike, commanders need knowledge. The Global Hawk setup process turns a giant unmanned aircraft into an airborne scout, giving military leaders distance, time, and awareness before danger arrives first. Its scale also changes how crews plan. A normal sortie may cover hundreds of miles, so each route, sensor task, weather update, emergency field, and communication handoff is reviewed before the aircraft departs. The Navy faced a harder problem when it began putting unmanned aircraft on carriers. A land runway is stable, wide, and predictable. An aircraft carrier is moving, rolling, surrounded by wind, and crowded with sailors, jets, fuel hoses, tractors, and weapons crews. For an unmanned aircraft to operate there, it must fit into a complex military workplace. The X-47B Unmanned Combat Air System demonstrator proved the concept could work. Its tailless flying wing shape looked very different from traditional Navy aircraft. Instead of a cockpit canopy, it had smooth surfaces, folding wings, and a compact body shaped for low observability and carrier handling. When the demonstrator was placed aboard USS, Harry S. Truman crews had to prove that an unmanned aircraft could be moved, parked, secured, and handled safely on a flight deck. The process begins with choreography. Flight deck crews use hand signals, control devices, and constant awareness to move aircraft within inches of danger. Jet blast, tie-down chains, elevator edges, and launching equipment all create risk. The X-47B had to respond without a pilot inside, while sailors treated it like another aircraft in the cycle. On May 14, 2013, the Navy reached a major milestone when the X-47B completed the first successful catapult launch of an unmanned aircraft from a carrier deck. The aircraft was attached to the catapult, checked, held in position, then thrown forward by the ship's launch system. Seconds later, it climbed away from the carrier under autonomous control, proving that unmanned aviation could survive the violent acceleration of naval launch. The program kept advancing. The X-47B also demonstrated autonomous carrier landings, a difficult aviation task, descending toward a small moving deck to catch an arresting wire at the correct angle and speed. Then, on April 22, 2015, it completed the first autonomous aerial refueling of an unmanned aircraft, receiving more than 4,000 pounds of fuel from an Omega K-707 tanker using the Navy's probe and drogue method. That refueling test showed why carrier drones matter.
And that was at time 55, so it's staying pretty strong.
If an unmanned aircraft can launch, recover, and refuel without a pilot on board, it can extend the reach of the carrier air wing, take on dangerous missions, and free manned aircraft for other tasks. The X-47B was not built as a frontline fleet aircraft. It was a pathfinder, proving that the carrier deck could accept autonomous aircraft and that naval aviation could move beyond traditional cockpits. The next major step became the MQ-25, an unmanned carrier aircraft designed around refueling. Modern carrier strike groups rely on fighters, But those aircraft need fuel at long range. When manned fighters must refuel each other, the carrier loses aircraft that could otherwise be carrying sensors or weapons. An unmanned tanker changes that equation. The MQ-25 Stingray was developed to become the world's first operational carrier-based unmanned aircraft. Its initial mission is aerial refueling, extending the range, endurance, and power projection of the carrier air wing. Instead of sending a pilot into a tanker orbit near potential danger, the Navy can use an unmanned aircraft to carry fuel forward and support fighters before they return to the ship. Aboard USS George H.W. Bush in December 2021, the Navy carried out an unmanned carrier aviation demonstration with the MQ-25A prototype. The event mattered because a carrier is not just a runway. It is a moving airport, repair facility, weapons platform, and command center. The catapult system launches the unmanned tanker just as it launches manned naval aircraft. Once airborne, it can move toward a refueling area, meet a fighter, extend its refueling equipment, and pass fuel through the probe and drogue system. In June 2021, the MQ-25 test aircraft refueled an FA-18 Super Hornet, marking the first unmanned refueling of another aircraft in flight. The fighter successfully closes behind the tanker, plugs into the drogue, and receives fuel at high speed. For the Navy, that capability strengthens the entire carrier strike group. Fighters can fly farther, stay airborne longer, or carry more combat load instead of extra fuel. The carrier can operate at greater distance from threats while still projecting air power. The MQ-25 proves that unmanned aviation is not only about surveillance or strike. Sometimes, the most important robot in the sky is the one that keeps every other aircraft in the fight. The future of carrier aviation depends on preparing old ships for new machines. Nimitz-class carriers were designed during a different technological era, but they remain central to U.S. naval power. During maintenance periods like USS Theodore Roosevelt's docking planned incremental availability, workers inspect, repair, modernize, and upgrade systems for future aircraft, command networks, sensors, and unmanned operations. These upgrades matter because drones and future vertical lift aircraft require more than deck space. They need data links, control stations, maintenance areas, support equipment, software integration, and sailors trained to operate alongside autonomous systems. A carrier that once launched only manned jets must prepare for a mixed air wing. The Navy also created a dedicated organization to advance unmanned aircraft testing. On October 18, 2018, it commissioned Air Test and Evaluation Squadron 2-4 at Naval Air Station Patuxent River's Webster Outlying Field. Known as UX-24, the squadron became the Navy's first dedicated unmanned aircraft system test and evaluation squadron, operating more than 23 fixed and rotary wing systems, including Fire Scout, Puma, Blackjack, Aerostar, and commercial drones. That step shows the shift. The Navy is no longer treating drones as side projects. It is building units, procedures, test teams, and upgrades around them. From the RQ-4 Global Hawk, watching from high altitude, to the X-47B proving autonomy at sea, to the MQ-25 refueling fighters from a carrier deck, unmanned aircraft are becoming part of military aviation. The process is technical, slow, and demanding, but the goal is clear. Give commanders more reach, more endurance, and more options without putting a pilot in every aircraft. That's the end of this video. I hope you enjoyed it. Make sure to subscribe to this channel so you don't miss any of our new content. See you next time.